Buenas tardes. How's everyone doing? I looked at the test grades and you did quite well as a group, even individually, of course. What I'd like is for you to let me know any of the problems that you want me to review, that you were not sure of the answer, and I can look at that. So let me know your comments on the test. So Valeria, Gabriela, Alexandra, good afternoon. So next Saturday will be another test, and provided there's no interruptions, it should just be a 6-hour block of time. We'll see how we progress this week. No comments? It was fair. It was not fair. Which problems were challenging? Let me see which one was answered the worst. So the question that was answered the worst was the one about the online distance education, and the answer there being the observational study. Because there's no randomization. Okay, there's no randomization. So that's just an observational study. You should have the solutions. You should have the answers. The system should tell you which questions you got wrong or right. Have a look at that, okay? And then we could talk about it tomorrow. So I can just get started today. So at the beginning of tomorrow's class, make sure you review the answers, your grade on the test, which ones you got right, which ones you got wrong. The system should be able to tell you. If it doesn't, let me know. I'll see about the settings. Okay. So you have an idea of what's expected in preparation. And so this test coming up will be a NOR and regression and probability. So there's more material. I should have more questions on it. And we'll see about the time. We'll discuss that closer to the weekend. All right, so we left off here. This looks really messy now, but when we went through it, I hope you followed my discussion about percentiles and how we read percentiles off a relative frequency histogram or a density curve that is smoothed out around it. And I mentioned that x represents the random variable, and the little x is the value found here along the timeline. All along here. These are lowercase x. The properties of density curves come from those of relative frequency histograms, namely the area under the density curve is 100% or 1. And about the test, I withhold the grading until after the test is closed. Just, so that everyone gets the grade at the same time. All right, second property of density curves. Notice I talk about the area to the left, the area between, and the area to the right. But I don't talk about area or density at a point. So something like the chance that x, the random variable, takes on the value 50. So if this was for women's heights in inches, this is 50 inches. The chance that it takes on exactly 50, well, this is a continuous distribution. As a continuous distribution, we only see density between values, like on the left, the right, or between values, not at a precise point. And this will become more relevant later. But for now, when you see on continuous distributions a question asking for the density at a point, the probability, the percentage, the frequency, the proportion, asking for P at a point, the answer is 0. So this is when you think about being at any specific value. Let's say this was 50, then it would hard to because it's continuous and fractions or decimals make sense. It's virtually impossible to talk about density just at a point, because it's bounded by values that are just next to it. In any range of values, there are infinitely many values in a timeline. Infinitely many. So the chance of it, one way you can think of it is the chance of being at just one specific value is so small, it's 0. Okay, so the third point is with regard to what we discussed already last class about percentiles. We interpret the pth percentile as a value such that p% of the area under the density curve lies to the left of it. And I talked about percentiles before when we were talking about the 25th and the 75th percentile and the 50th percentile as well. So I explained last class that if the area to the left is 50%, then we call this value 64 the 50th percentile. If the area to the left is 10%, we call the value 50 the 10th percentile. So I could ask a question. This question is asking for what is X, or what is the 25th percentile. Now you'd have to have information to be able to identify where that is. And X would be along this timeline here, or this not timeline, but number line. So you would have to know either the rectangles, you'd have to know something about the rectangles to be able to do that. So what value of X puts 25% on the left? That's the sort of question I can ask you. So this is known as a backward problem. When I ask you for the probability, that's a regular problem. The backward problem is when I give you the probability or percentage or proportion or frequency, however you want to term it, and I asked you for the value of X. I have names for all of this. In a moment I'll get to it, but the regular problem would be probability a regular problem would be I ask you for the area, I ask you for the probability. In this question, I'm asking for the percentage or percentile. Okay, so these are the ways we use density curves. We're going to cover normal distributions today. Tomorrow we're going to cover regression, least squares. And by Wednesday we should get to probability. That's a longer unit. All right, so the final point, and I mentioned this already, Because density curves are idealized, we imagine that we have all information possible on the variable when we are smoothing out the underlying relative frequency histogram. When density curves are symmetric, we have a special name for the center or mean of the distribution. We call it mu, or the Greek letter for M. And it looks like a U with a long line, or it looks like an M. If you squint your eyes, you can see it's an M. And the special name for the spread of the standard deviation, or the standard deviation, called sigma. This is the Greek letter S for sigma, lowercase sigma in particular. Because there's another kind of sigma. This is uppercase sigma. And you've seen that as a summation, S for summation. They're both sigma. One is lowercase, one is uppercase. All right. Now, because the density curve is symmetric, the center is around the mean, and we refer to the spread as the standard deviation, or sigma. So that brings us to discussing normal distributions. What are normal distributions? Normal distributions are a particular set of symmetric distributions that have a single peak, and they have what is called a bell shape. And these are density curves, but in addition to density curves with the 4 properties above, I'm going to demonstrate the other property that it has. So if it has this property that I'm going to describe, you can refer to that density curve as approximately normally distributed. So it's in reference to the way it spreads out. Now we know that it's going to be symmetric. Being symmetric, the mean is in the middle. And I can draw the peak over here. I'm trying to find the right place for it. I think here's fine. And now I want to draw a bell curve around. It turns out for a normal distribution, the way that it is spread out is so that, I'm going to move that over a tad. Is so that it is concave until where? Where's this line? This line marks 1 standard deviation away. Now we talked about 1 standard deviation away, but we did that when we were talking about using the sample standard deviation, the sample mean. Well, because we believe we have a good representation of the population, we're going to call the standard the mean, the sample mean mu, and the sample standard deviation sigma. So we're going to say, well, we believe that the population data would look similar. And there's an inflection point right here, 1 standard deviation away, from which the curve turns up. Now the rest of the distribution is described by how spread out it is after that. So beyond that, And in between, these are supposed to be equal distances. Let's do that again. So this is 2 standard deviations away on both sides. So for a distribution to be normal, 68% of the observations should be surrounding the mean. So that's most of the data. If you remember our example with the, what did we look at together? With Ruth's data, right? We looked at Ruth's data together. And with Ruth's data, because it was symmetric, we found, I think it was 67% of the observations were within 1 standard deviation. But then I asked you to check 2 standard deviations. In that case, we had all of the data. Well, then that's not a normal distribution. A normal distribution will have 95% of the observations within 2 standard deviations. So it's almost all of them. So in the middle, we call that most. And then within 2 standard deviation, you find almost all. And then within 3 standard deviations, you find does anybody know? Did you read ahead or do you know this? What do you find? Right. And Yvette says it's 99.7. So really, virtually all except what? That includes all observations except what we call outliers. Okay, remember 3 standard deviations for a symmetric distribution, we're going to call those outliers. Now with Babe Ruth's home run hits, there were no outliers. Everything was in 2 standard deviation that was very tight. A normal distribution allows there to be some outliers. What's the proportion of outliers that there are in this distribution? What proportion of values are outliers? So this is normal in the sense it's a derived distribution that characterizes many phenomena that where it's mostly symmetric, but it allows for some outliers, it allows for some extreme values. What proportion of values are outliers? Close, Gabriel. Oh, I see. You did 3 out of 1,000 or 0.3 out of 100. That's right. So what proportion? He's correct. So it's going to be 0.3% divided by 2 on this side and 0.3% divided by 2 on this side. Or 0.15%. So I just got to be careful about writing the percent. And Gabriel just said he didn't say percent, but he did anyway. 0.15% on both sides. So it's symmetric. So whatever happens on one side happens on the other. So you do see, like he says, you're going to see out of 1,000 observations, you can expect how many outliers? What's the blank? So remembering this is a percentage, right? So this is 0.3% is 0.003 times 1,000. So that's 3. Very good. So you want to know, if there are 2 over here and 1 over here, but it's it's an approximation, and it doesn't have to be exactly. This is an approximation. So if you had a distribution and you drew it, if you had data, and you graphically depicted the distribution and it looks symmetric, you could calculate the mean x bar and the standard deviation s and check these properties. What percentage of observations are within 1 standard deviation, what are within 2, and what are within 3? And you could take an executive position and say it is normally distributed approximately, if this is true, or these points are made true. Okay, so that is a normal distribution. There's more detail to it. You could find out, in Excel, we could talk about properties of a normal distribution. You could ask for my equal sign, and you see the pop down. I get rid of this. I can't get, hold on. Okay, so you see all the different normal distribution options here. You can use normal distribution, norm.dist. And what does it ask for? It asks for the mean. It asks for which value of x you want. The mean and the standard deviation, those are the parameters of the distribution. And then you tell Excel that you want the percentile. You want it to add up the density to the left. That's cumulative. So if we did this for a distribution, we need to know x, the mean, and the standard deviation, and pick cumulative. In that cumulative, you put 1 or 0. So we'll talk about that more later. But you can use Excel to make calculations to get more precision than this. These are just 3 broader categories that you can check between 1, 2, and 3 standard deviations, but what about in between? You know, you can. So let's look at an example, and I'll explain this again. Before I get there, I want to remind you or clarify that a distribution like that shape and a distribution like this shape could both be normal as long as they both satisfy the property of a normal distribution, known as the 68, 95, 99.7% rule. Now, what is the difference between these two distributions? How would you characterize the difference between them? Let's say they were both normal. Let's say the means were the same. Let's say the mean had the same value. Make this a little more similar. Let's say they were the same. So what's the difference between these distributions if they're both normal? So I'll call x, the random variable x, normal, and the one y normal. This is the symbol to mean, that means distributed normal. It's a tilde sign. So the difference between these two, if they have the same mean, to be normal, the inflection point is like over here, right? I can call it sigma y. And here the inflection point is over here. Me and Mike are roughly. My drawing's off. It's not perfect. I better fix it. It'll be confusing. Should be symmetric. So what's the difference between these two? It is the standard deviation. The standard deviation of this one, of y, is much bigger than the standard deviation of x. That's the difference. the range of x, or the standard deviation of x and y differs. So we say the standard deviation of y must be bigger than the standard deviation of x. It means that still, if they're normal, then 68% should be in here, but also 68% should be in here if it's true that these are both normal. And then, and then 95 and 99.7. So we have the same interior in terms of proportions, but the different shape to mold it, I can mold it differently, but then the peak has to drop down. To put 68% with a wider range, then this has to come down from here. Okay? So these could be both normal, but this is the only way they could be both normal. And their difference is the flatter one has a wider or larger standard deviation, more spread out, greater range. So if these were returns, if these represented percentage returns on an investment, and you prefer certainty, which one would you pick, X or Y? Okay, Valeria says X because it's tighter, it's more predictable, right? This is more like Ruth. Much more predictable possibilities. This is much more spread out. So if I actually put numbers on here, it depends, but I put them both at the same mean. That's what helps me make a decision here. So this one is less volatile. Less risky than Y. Good. All right, so next we're going to refer to this rule as the 68, 95, 99.7% rule, and we're going to remember that 68% of the data lies within one standard deviation from the mean, 95% lies within 2, and 99.7% lies within 3. And this curve is actually a function that we're going to talk about, and that is used with calculus to determine the areas to the left at any point. So you could actually get those. That's why Excel has those values, because it can approximate the area under the curve to the left at any value here, not just 1 or 2 or 3 standard deviations away. But this is what we use, just roughly speaking, to speak about the distribution. And here I've just done another drawing that you can practice, laying out the distribution here. And I want to make the point that since all we need to know to draw the normal distribution are mu and sigma, those are two parameters of the distribution that define it. And that's all we need to know. We need to know that it's normal or approximately normal. We need to know its mean and its standard deviation. And that's enough to estimate the probability of certain outcomes. Isn't that fantastic? So this is the variable x. I can talk about the function y on that curve I can talk about the function y as where this is x, this is the value, and this is y. This is like the height of this curve. And it would be defined as this. This is the function. Now, I'm not going to ask you this again, but I just want you to realize this is a function, and look at it in particular. You see some things that are familiar. You see the exponential function. You see pi. So you know those integer, not integers, but those values, right? This is 2.17. This is 3.41. So you recognize those. What else is here? Look, you have the mean and the standard deviation and x. So you have a form of a function. You have some known values, and then by changing x, as long as you know the mean and standard deviation, y will change. So in that way as well, all you need to define the function are mu and sigma, and knowing that it's this functional form. So I'm not going to show you that again, but basically what happens and what Excel uses is this function, and if you want to know the percentile, that's how you would write it. And to find that, Excel, you could ask Excel, telling it the mean and the standard deviation, it will be able to find that for you. You'd have to know that it's normally distributed, its mean and its standard deviation. And you'd find that area. Okay, so let's look at an example. I'm going to have trouble with putting these together again. There we go. Okay, so here's my example. There are 100,000 height measurements of women 18 and over in Puerto Rico. The sample mean is 64 inches and the standard deviation is 2 inches. So let's say you made a histogram and you saw that the distribution was relatively symmetric. It had one single peak. It had a bell shape. And so we assume that the height of women is normally distributed, but we should do a check. Right? We should check that 68% of the data is within 1 standard deviation, 2 are within 2 standard deviations. Sorry, 95% are within 2 standard deviation, and 99.7% are within 3 standard deviations, leaving 0.3% outliers. So what we're going to do here is draw the distribution, but with the values included. So in the middle would be 64. I'm not sure why I left so little space here. And then over here, say it's 64 with just standard deviation of 2, so this would be 66. This would be 62. This would be 68 and 70. Let's just say it spreads out like that. And then this is 60 and 58. And I will mark I have to fit it in, so so that's 68% of the data. That's 95% of the data. And that's 99.7%. And then we say, I can write that x between 62 and 66. So when I write expressions like this, as I discussed last week, this is called in between, right? Where you have a smaller number, a larger number, and the x in the middle. So between 62 and 66%, you find 68% of the observation. So that's how we write it. Between 60 and 68, we find 95% of the data. And between 58 and 70, we find 99.7% of the data, or 0.997. And I can ask other questions as well. And here's just some examples. Would I also know the probability that x is greater than 66? Well, I can make a sketch. And I want to know, what is the area to the right of 66? How would I figure that out? I know that between (62) and 66 are 68% of the observations. So that means outside of this range are 100% minus 68%, and on this side, divided by 2, this must be what? Remember to refresh your screen if it looks blurry. Right, Yvette. So this is going to be 16%. This is also going to be 16% over here, and it fills the entire space. So we can use this as a tool, this rule as a tool and the interpretation is that 16% of the observations are above 66, or we can also refer to that as probability, and that means we say so there is a 16% chance of a height being greater than 66 inches. So on the next, and observing the next female to walk into the mall, into a mall, either Plaza or the Mall San Juan in San Juan, the chance of her being taller than 66 inches is 16%, if this was true. Yes, percentage. How do we do this on Excel? We would have to tell Excel the information that it's a normal distribution, that the mean is 64 and the standard deviation is 2. But in addition, we have to tell it, are we looking for the cumulative distribution or not? Now in this case, this is looking to the right side. The cumulative is the left side. It's the percentile, or the percentage to the left. So we need to make an adjustment when the arrow goes this way. We need to make an adjustment Does anybody know what I'm talking about? Let's see. So we're going to put in here normal dot distribution for 66. Where the mean is 64 and the standard deviation is 2. We do want cumulative. And that's the value cumulative. So it's much more precise. What is that giving me? 84%. Notice what I did. To get cumulative, I put a 1, right? I entered 1 to say yes, cumulative. So that's giving me the area to the left. So if you're using Excel to get the right answer, you would have to say 1 minus that to go over here. And that's you have to be aware of which side you're on, and you know that by the arrow here. Okay? So you would take 1 minus probability x less than 66, which you would be getting out of Excel, 0.84, and then you get 116 or 16%. So those are two ways to do this. You can use Excel, or you can just use this rule that I've taught you. You get the same answer. Maybe this one's faster. You should know both. You should be comfortable using both. What about this question here, 58? So I'll draw it. You should always sketch. And I want to do this for the same distribution, so 64, and then 62, and then 60, and 58 is all the way over here. So what do I know about 58? And I look left because this arrow is left. What do I know about 58? Well, I know that it is paired with '70, where 99.7% of the observations are between, but that means 100 minus 99.7 divided by 2 should be the area to the left here. So knowing my property, the 68, 95, 99.7 rule, it's at 3 standard deviations from the mean, and this would be 0.15%. And that's the answer. Then let's try it in Excel. So this should be straightforward because we're going to the left. We tell Excel all we're going to do is change x to 58, and we should get the answer. So I'm going to change x to 58, and we expect it to be 0.0015, right? Approximately 0.00135. It's more precise. Excel will always be more precise. I'll put it on the side here. So in Excel, So this rule that we have that 68, 95, 99.7% is a rounded, they rounded up. Even if I round here, I don't get 1.5, but anyway, it's close. More like 0.0014. All right. Okay, so then you can continue to answer these questions and just using the rule. What about 60? I'm going to mark the major tick marks. 64, 62, 60. So that marks 2 standard deviations away. And I pair it with 68. And I know between these two are 95% of the observations approximately. So if I want to go to the right, that's going to be 100 minus 95 divided by 2. So that's that's 2.5% or 0.025. We can try that one in Excel as well. We're just going to change x to 68. We could do it for 60 as well. This should give you the same answer, right? So if we go to Excel and we change x to 68, but we have to do a 1 minus the cumulative. Because the cumulative will be what? Let's see. So if I change this x I'm changing it to, oh wait, I did something wrong. I just realized that's not 60, that's 68. Sorry, I realized. Okay, so where were we? 60. So we found out that x is greater than 68, and 60 would give me, this is not what I want. I want to go this way, so let me erase that. I apologize. I was looking for 68. But I was trying to pair it, and now we have to see what to do. So I pair them together, so I know that in between is 95, but I want to get I want to go to the right of 60. So it's going to be 95. And the reason why I found this is because I need to include that, because that's greater than 60. And I'll just put it back in, but in this context, this would be 100 minus 95 divided by 2, which was 2.5%. So now we know the answer is 97.5%. You have to add those two together. You're talking about, Nivette, question 8 after this is question 3. Okay, so if I was to do this in Excel, remember that if I want to use Excel, Excel only gives me the left side. So then to find the answer, we have to subtract it from 1 to find this. So back to Excel. Oops. I'm going to put 60 in here. And you get 0.02275. So the Excel solution you want to take it 1 minus whatever you get for x less than 60. So this was 0.227. What was it? 2275. And then you get just about the same answer. So notice our Excel is more precise. These are rough estimates using the rule, okay? Sorry, I wrote it wrong. It's 97725. So 97.7%. So they're a little bit off. The correct one is the Excel one, but if I ask you to use the rule, you just use the rule, and that's the answer. Okay? And then I have a bunch more here. For number 8, Yvette, remember the property for density at a point. For a continuous distribution, this is always 0. That's just 0. if that's your question. Okay, so what about these? These are around 70. All of these are about 70, and then 62 to 64. So let's make a drawing for 70. And dissect it. So where's 70? So 64, 66, 68, 70, 62, 60, and 58. And I want to go less than 70 for the first one. What do I know about 70? I know between here and here, between 58 and 70, you're at 3 standard deviations, so that's 99.7%. So if I want to go less than it, I am going to get all this area, including this tail here. What is the tail? The tail will be 100% minus 99.7% divided by 2. So we've already done this before. This one is 0.15%. So you need to add those two together to find all this. So the chance of seeing a woman's height smaller than 70 is very likely. 70 inches. What is 70 inches? 70 inches. It's very tall, right? It's over 5. It's 5, almost 5'10". 5'10". So almost all women are going to be that under that height, right? Women are not that tall. So 99.7 plus 0.15 is 99.85. You can use decimals, you can use percent. I'm fine with either. Now what if we want to go the other way? We want to go greater. Well, if it's greater, it's just 1 minus what we got on the other side. So this is 1 minus 0.9985 on this side. Which we already know anyways because of the symmetry. We know it's 0.15 on in each tail. So this is going to be 0.15. So we know quite a bit just knowing about 3 standard deviation spread. What about this? X greater than or equal to 70. What does this mean? This means both means both x greater than 70 and x equals 70. Well, we know this is 0.15%, and we know that this is 0. There is no density at a point, so 0 adds nothing, so the answers are the same. So often you'll see for continuous variables, they can either be written like this with an equal sign or not. The equals adds nothing. No density, no area. And that brings us to the last problem. What about being between 62 and 64? Again, I emphasize, I keep drawing them because I want you to draw these. These are easy problems compared to where we're going with this. Not that it gets much more difficult, but practice drawing the easy ones. So here we have 64 in the middle, 66, 62, and I want to know between 62 and 64. So now what? What's the chance of being between 62 inches and 64 inches? So this is 6 foot 4 inches, and this is 6 foot 2 inches. So I always write the smaller number first, and I use the sign small to big, with the X in the middle. This means in between. So I know between the two of them, between 62 and 68, 66 are 68% of the observations. So half of 68 is 32. So you should feel like every answer that we solved is a little bit different, but it's all related to the same distribution, the same layout. Oh, did I say 32? 34, thanks. And the last one I mentioned is x equals 82 is 0. Any questions so far? So you should feel like, okay, I get it, but it just looks like we're doing it different every time. I want to find a more systematic approach. Before I go there, I want to show you a more systematic approach. But before I go there, I have to talk about the backward problem. This is where you try and find the x that corresponds to this percentile. And I know it's a percentile because it's looking for the area to the left of a value. So I should draw that. Always draw, and even more so draw when you're working with percentiles. Me and my color scheme. Now I need to mark small x such that less than it are 97.5% of the observations. So the chance relative to x or less than x is high, right? So if I was here, the area to the left of here would be 50%. So I need to go further and further over. So I'm going to mark it here. So I put on 9750 at the top, and I put on x with a question mark. That is capturing what the question says. That's an illustration of the question. Now this should look familiar. We did get this in one of our answers. If we go back, where did we get that? It was here. We got it there. But that's going to the right. If we went to the right of 60 or the left of 68, which is its pair, we would have that answer. So you could do this by trial and error, or you could do this by memory, that if this is 64 and this is 66, for this to have 95% in the middle, and then 2.5% outside, this must be 68. So again, you should feel a little bit, unless you really get this, a little bit uncomfortable because it looks like I'm doing things differently every time. You fumble through and you find your answer. So my answer would be x equals 68 inches. I further make my case with questions like this. None of these numbers are precisely on the, applying the rule or the larger tick marks. It's somewhere in between. 55 is way down here and 65 is over here. You could approximate it, but it doesn't feel that, you don't feel that confident or comfortable with it. And then, so I'm not going to answer that. I'm just trying to make the point that we need a better tool than just this. This is going to get us somewhere, but we want more precision. We have Excel, but if we were to do this manually without Excel, I want you to be able to have a technique as well for that. So, also a question like this is not so straightforward. Let me make it a little bit bigger so you can see. Find the values of x. So this is a backward problem as well. Find the values of x for where 68% is, between them is 68%. So the probability of a woman's height being between these values is 68%. Well, we know at least one pair. We know that if it's between 62 and 66, this is 68%. We know that. But there's other places too. There's actually infinitely many places or heights that you have 68% of the observations. I don't want to make it look too different than the others. So here, So you could say this is this is 68%, right? Like we've been doing. I made it a little bit broader looking. Can I move that in? But I could move both of these over. I could move. I can't really move it, but anyway, so that's 68, but I could also say that maybe, you know, being over here and here is also 68. There's infinitely many places, positions between which I can make 68% of the observations. But because of the larger tick marks, I only know about these two. So we need a more general approach to solving problems that aren't just centered around these positions, 1, 2, and 3 standard deviations from the mean. Okay, and finally, I'm going to make a point. No, I don't know what to do with these. I have to be careful about using those. Okay, so there's a last problem here. What about x greater than 40? If x is greater than 40, where's 40 on this timeline? 40 is way over back here somewhere. We can answer that in general, that likely all women are taller than 40 inches. So this is probably close to 100%. But again, maybe we want more precision than that, all right? So to get there, I'm going to introduce this other normal distribution. This is a specific normal distribution. It's called the standard normal distribution. And it's really nice because, well, sketch it yourself. A standard normal distribution has a mean of 0 and a standard deviation of 1. So 0 is in the middle, and then 1, 1, 1, and 1, 1, 1. Those would be the standard deviations, and they would put me at 1, 2, and 3, and -1, -2, and -3. So what's great about this, it has the properties of a normal distribution. We call it Z just because we're going to use it in a special way, and it's It gets its own name for that reason. It's a special standard deviation, or sorry, it's a special distribution. So this is Z now. And what's really interesting is that the value that it takes tells you where it is relative to the mean. So 0 is the mean, and so it positions the number line right at the center. And 1, which is the standard deviation, denotes 1 standard deviation from the mean. And 2 is not just the value 2, but it tells me how far it is from the mean. It's 2 standard deviations from the mean. And 3 tells me it's 3 standard deviations from the mean. And then in the reverse, -1, -2, and -3 standard deviations from the mean. So I get that extra bit of information if I talk about a standard normal distribution. Then anytime a number is mentioned, if let's say Z is equal to 1.75, you know how to draw it. It's over here, but you also know that it's 1.75 standard deviations from the mean, which is important. Or above the mean, 1.75 standard deviations above the mean. And so we can go beyond the broader tick marks right inside, because it tells me, and I can use this in the standard normal, as a standard normal distribution. I have much more detail about the distribution provided in tables that I've given you, but also you have it in Excel. So I'll show you, these are the tables here and how to use them, and then I'll show you in Excel. So here is the first of 2 tables. This one has all negative values of Z, you see, and again each one tells you how far you are from the mean. It begins with -3.9. That's the furthest you can be away. -3.9, that's the first decimal, and that's the second decimal over here. First decimal, second decimal. So on the graph that I have here, it's symmetric, it's centered at 0, and the furthest on the chart, I mean, you could go as far as you want, but 3.49 is the smallest or the most negative value that you have on the chart. And that indicates that inside, so inside the chart corresponds to the area under the curve. Now the curve doesn't seem to be over here, but it is. It's slightly over here. And under there are 0.0002% of the observations, or sorry, 0.0002 or 0.02% of the observations. So I'm going to mark that as this area to the left. Let's do it in black. Is 0.0002. It's always 4 decimal places. That corresponds to 0.02%. So it's in the outliers. It's among the outliers, this -3.49 standard deviations below. Now this chart goes all the way up till 0. You can see as you go down, the chart ends at 0 here. At 0, the area to the left is 50%. So that makes sense. Questions? So the area in here is the area to the left. So really this is a chart of percentiles. So these are the percentiles and these are their corresponding area, or the percentage to the left. Let's go to the positive chart. Oh, just one other thing. So going through this, you're going to do this like So going from left to right is the same as going in the chart from right to left. Because it's negative, we're going to go backwards. So it's like reading in Arabic or reading in Hebrew or Chinese, right? It's backwards as well. It's interesting. So they read, I think Chinese read backwards. I actually have to verify that. So anyway, reading backwards on the negative table, because you're going from negative 3.49 and then higher and up. And that corresponds to moving in this direction, right. Now to the positive table. The positive table starts at 0 and what's the highest value on it? The highest value on it is positive 3.49, and the area to the left of that is almost all of the data. If you go to the bottom, it's 9998, right? It's going to be the inverse. Look at that. I lost my... Okay. So to be the left of that would be (0.9998) to be to the left of that. So how would we write that? Probability that x is not x, actually z, right? This would be big Z less than 3.49 is equal to 0.9998. That's how we would express that. And then similarly here, we would express the P that Z is less than negative 3.49 is equal to 0.0002. All right, so those are how you use the tables or read the tables. Notice on this table, we're going to move from left to right in the regular direction. So you're going 0.00, 0.01, 0.02, all the way to 0.09, and then to 0.1. So you're moving always this way. And the shaded region is reminding you you're getting the area to the left. So that's the standard normal chart or table. Let me show you in Excel. Notice, so this was for the normal distribution. And notice that we use the first one. The second one here would have been to do an inverse problem or a backward problem. We didn't end up using that. We will. I need to erase all of this. The standard normal distribution would be this one. It has an normal.s.dist. What did I do wrong? Okay, so it won't calculate because I can't make it bigger. It won't calculate because I didn't put numbers inside. But if I did put numbers inside, we want the area to the left of 3.49. Let's try that one. 3.49. And you want it to the left, so you put a 1 and then return. And there it is, 0.9998. That's the last calculation I did, or the last lookup that I did on the table. Okay. So, oh, I didn't want to go out. So let's get back to where we were. So how am I going to use this now? So what I'm going to do now is use this table to help me solve problems. We're going to refer to the z-scores or negative z-scores for table 1, that's the negative table, and we'll refer to positive z-scores as those on table 2. And let's begin by checking. Let's check that the rule, the 68, 95, 99.7% rule applies to the standard normal distribution. So let's check if this is 68%. How do we check that? Well, I want the area between -1 and +1. On the standard normal curve. So -1 would be here, 0 here, and 1 would be here. So to figure this out using the table, and I'll show you the table in Excel. So you need to know the skill of using the table, because statistics is done with a lot of tables. It's just important to understand the distributions. So the way I'm going to show you to use the table will be to compute two probabilities. You want the probability that that z is less than 1 and the probability that z is less than -1, and then what you're going to do is find the area in between them. So right now I'm ignoring the fact that I know this is supposed to be 68. I know this is 68%, I know that answer, but I want to use the table to get that answer and check if the table has the same answer, right? So I know it's 68, but let's verify. So let's get the area to the left of -1, and then we're going to get the area to the left of +1, and we're going to subtract the big number by the small number. And cut out this area in between as a result. Or mark, or demark that area. So let's go to 1 and -1. Let's do -1 first. So going to -1, we're looking for -1. Here it is. So -1, it's 0.1587. 0.1587. What about +1? +1 is the area to the left, given in the table, is 0.8413. So we have 1587 and 8413. We take the larger area minus the smaller area, and it leaves us the area in between. When I say 8413, that's going all the way back. So this should be 68%, is it? It is to 4 decimal places, and then just to 2, it's also 68%, so it's true. So this is how we use the table, and I just verified that the other information the 68, and we're going to check 95 and 99.7% within 2 and 3 standard deviations. But in this case, within 1 standard deviation, this property is contained in the table, and so much more. I can check for 2 and I can check for 3. My sketches aren't always perfect. So that's 1 and 2, 1 and 2. So between 2 standard deviations below and 2 standard deviations above the mean, what do we find in the tables? At negative 2 standard deviations, the value is 0.0228. At 2 standard deviations, the value is 0.9772. Exactly, Valeria. So then our result is 0.0228 for this one and 0.9772 for this one, and I subtract the big one by the small one, and get my answer. So this is to 2 decimal places, to no decimal places, approximately 95%. So again, the property that we learned that within 2 standard deviations you find 95% of the observations is contained in the very detailed Z tables. And finally, we have for 3 standard deviations, you can verify. I'll do this last one. Well, my drawings look different slightly. Doing my best here, but they should be the same. So I'm going to check what happens at 3 standard deviations from the mean. At -3, that puts us 0.0013, and for +3, 0.9987. So 0.0013 and 0.9987. Do you notice these numbers are complementary to each other? One comes from the other. You should see the pattern by now. They're related by, they add to 100%, or 1, sorry. So this one is 0.0013 and this one is 0.9987. And that's because they have to add to 100% or 1. Because this is symmetrically the same as this area. So finally, take the big value minus the small value. And you get (0.9974), which is what we expect for 3 standard deviations, the area between. All right, so it works. So these kinds of exercises, these were examples, but I used it to verify something I knew should be the case. And with those examples, you should be able to solve these problems that I refer to as type 1 problems. These are problems regarding the standard normal distribution that you solve using the techniques I showed you with the table. So you guys can try these. And there's videos about this you can watch. The videos on this material. So you're just reading the table. This is just a matter of reading the table. This will be the area to the left. This is the area to the right, and then I repeat it. Okay. So you should be able to do all these problems. Let's just try. Let's do this page anyway. Let's do this. So let's start with number 6. So the probability that Z is less than 2.27, so that would be around here, 2.27, and I want to go less than it. So let's check out the table. I need the positive table, and I check 2.27. Two point two 0, 1, 2, 3, 4, 5, 6, 7. It would be this value here. And you can see that it's in the column for this second decimal here. So 0.884. Sorry, I have to check that again. Was it 0.884? 0.9884, sorry. 0.9884. So 0.9884. It's very straightforward. And then if I wanted to go for the negative, so look, if I change the sign, it's going to be the same area. So if I change the sign to a negative and the direction that I'm going, because of the symmetry, I get the same answer. Okay. So if I go in this direction instead for the negative, and I want all of this area, that gives me the same answer. It should give me the same answer. But let's try it with the tables. If I look up in the table will give me the area to the left. So if I go for negative 2.27, negative 2.27 would be This one here. .0116. And then what you would have to do is compute 1 minus that. I'm going to erase this part because this might be a little bit confusing that I have that there. So you would take 1 minus 0.0116 and you will find that gives you the same answer as before, 9884. Okay, so changing the sign and the direction of the problem because of symmetry gives you the same answer. So that's how you use the table. You should practice that. You can also get these answers in Excel. So let's do this one in Excel, okay, with the standard normal. So 2.27. This is standard normal. I want to go to the left. All I have to tell the all I have to tell Excel is 2.27, and then I want for the standard normal and cumulative, the area to the left, and you get 0.9884. So it works. Remember, there has to be an S norm, S distribution. You should know how to do this problem, so just verify this one. Like I say, it's in the videos. Verify you know how to do that. We just did a bunch of those, so you should be able to do that. And then I just want to make a point about what this means. We're going to talk about area between and area outside. This is between. And in particular, this is symmetric, so I'm going I can write it like this, where the smaller number comes first and the larger number, and I use the symbols greater than, see? And I read this as z greater than negative 2.5, but less than 2.5. Or else in between, area between. You can also write it like this. Notice that you use the absolute values that get distributed to the 2.5 as positive and negative, and it turns into this. Okay, so that's area between. If you want to talk about the tails of the distribution, so the extremes, I won't say extreme because this is not exactly extreme, but it's in the tails. So this is how you would write it, and you would say either this is z or z is less than negative 2.5, or z is greater than 2.5, and you would write it like this, going outside. Okay, so this is the area in the tails. Outside of negative 2.5 and 2.5. So those are the two ways to write that expression. And you use the word or here, and you assume this means and in here. said greater than negative 2.5 and less than 2.5. Because z can be within that range at the same time. But here you have to say or, because you could either be less than or greater than. You can't be those at the same time. Okay, those are my drawings. This is between, this is outside. All right, so these are Z type 1 problems. This is where I give you the z-score and you tell me the probability. And you can try these too. Practice these, okay? Watch the video if you need help or you want to check your answer. Let me talk about this one. What is the probability that the z is between -4 and 4? Well, these are off the chart, right? So being between those two, the chance is 100%. It's going to be in between. Okay, so that brings us to the backward type problem. What about going backwards? So if you're told that the standard normal distribution less than a certain value was 0.4168, how do you find z? In other words, find the 41.68th percentile. So where would I draw that? I know the area to the left of the center is 50%, and this is smaller than that. So I guess that's going to position me somewhere around here. So when you do a backward problem, you have to take on the operations backwards. You write the probability in, and then you look inside the table rather than along the margin. For the z, you look inside the table and then out to find the z. So you look inside for 4168. I found it. Now you might not always find exactly the value, and I'll deal with that. you find the value 0.4168, which corresponds to negative 0.21. So it's very close to 0. Negative 0.21. So 0 is there, and this one is negative 0.21. Okay. Very good, Valeria. All right, so what happens if we don't get a value exactly as it's in the chart? I want to make this a little bit cleaner. Negative 0.21. Okay, so for instance, what about this one? How do we draw this? The area to the left of Z is 9098. So it should be somewhere over here, because you know, it's bigger than 50%. So maybe I put it too far, but okay, so it's about there. It's on the right anyways. And I want to find the Z corresponding to that. So to do that, I look inside the table and outside for on the margin to get the Z-score. So looking for 0.99, why did I put an 8 there? It's a 9, right? It's 0.9099. So we go inside and look for it. And it's going to be on the positive table. Allow me to clean this. So I look 9099, and the positive table runs like this, right? Regular way. So here it is. Oh, it's exactly there. 1.34. It's exactly there. 1.34. So I make it 1.34, and that's my answer. The next one, find the position happen with my drawing. Things get detached in odd ways. So for this next problem, it's a backward problem because I'm given the probabilities and asked to find the z-score. And here, between negative z and positive z, (6826). This should look familiar. This ends up being -1 and 1. How should I do that? If I didn't know the answer was gonna be -1 and 1, I would have to employ those techniques that we used before with 100%, or sorry, I'll just say 1, minus 0.6826 divided by 2, and put it here, and then carry out the rest. One minus 0.6826 divided by 2. That gives you the area to the left of 0.1587. So now look that up inside the table and out for the value, and you will find it. It looks familiar even. So looking on our chart, 1587 is on the negative table. That's why we do the drawing, to remind ourselves if we're on the positive or the negative table. And you see it's right here. It's exactly -1. So this will be -1. And symmetrically, because this one is -z, this one is z, this will be +1. So those are my answers. Well, my answer for what is z, it asks what is z, so z is 1. Okay, what about this next one? The chance that the area under the curve is greater than z is this small. So where does that go on my curve? It's a very small amount, and it's the area to the right. So it's going to be over here. Now I want to know what is the percentile. So either, if I look this up, what I'm going to get is the negative version of z, because the table only gives me the area on the left. So if I was to do this, if you look up 0.0026, if you'll be on the negative table, but I've had to adjust this from z to negative z to account for that. Remember, direction and the sign gives you the same answer, changing direction and sign. So looking for 0.0026 on the negative table, inside, right, we look inside, 0.0, .0026. So I have to go higher, right? 0.0026 is here. Negative 2.8. You see it's going to be a negative. So negative 2.80. Negative 2.8. So then this one must be positive 2.8. All right, so how could we do this otherwise? We would have to take 1 minus 0.0026 to get this area to the left. That would be .9974. And you look that up, inside and out again. So 0.9974 on the positive table, 0.9974 is going to be at 2.8 right here, as expected. So those are the two ways to do that. Now I have to pick the positive one because of the way this is written. It wants this one, whereas z, the area under the curve is greater than little z. That will only be for 2.8. So 2.8 is the 0.26th percentile. So when we did it this way, what we found was negative z, we have to convert it to the positive version. Or we do it this way. Oh, okay. Sorry, Valeria mentioned on the other row you have the same answer. So what do you do? What should we do about this situation? Working with the table, another answer is 2.79. So how do we reconcile this? This is important. So you'll find it gives you the same answer for the positive or the negative. So the solution, when that happens, since one is not better than the other necessarily, we go in between. And the final answer is that C is equal to 2.795, which is the average. Okay, so we can be more precise in a way, but inexact in another because we have two possibilities. We just go average between the two. We don't know that one is even better than the other. Okay. The same with this problem here. You need to pick the middle score for 0.9996. Let's look at that next. Does anybody have questions about this? Okay, let's try this one. If C is less than, the area under the curve less than Z is 0.9996. Let's look for that in the chart. Okay, so 0.9996, it's at the bottom. And it's all these possibilities. So which one is the answer? Neither is better than the other, I mean, necessarily. So we find a compromise between all of them by going into the middle. So what would be the middle value for Z? It would be in here. So it would be 3.3. And what is that? Second decimal. 3.355. You see that? 3.3. So it's going to be 3.3. So let me write it out. It's 3.35 or 3.36. So the best answer is between them, 3.355. Okay, so you look, again, the drawing, you look inside and out. I want the area to the left to be very high, 0.9996. And the question is, what is Z? And that's the answer. This is a backward problem. So when you have several to choose from, go in the middle. What do you do in this case? In this case, area to the left, have a look to see if it's there. So in all the other problems, we found the number inside the chart. But 0.9900, is it in the chart? Aha, it's not here. It's not here. And these are not equidistant to 0.9900. This one is closer. So we go with the closest one. When they aren't the same, or it's not exactly there, or it's not the same as what I'm looking for, I go to the closest one. So 2.33 is the answer. Okay, so they're not the same and they're not equidistant from 0.9900. This one is closest. So we pick 2.33. So all of this is made easy if we just use Excel, but I'm trying to teach you the mechanics of the standard normal distribution. So Z is 2.33. Or let me put it beside. pick the closest z-score. All right, what's next? So now we understand the z, the standard normal distribution. Let's do the last one, and then if you want to go ahead, you can watch the videos that come. So tomorrow I'm going to wrap this up in the first, hopefully in the first hour, I will finish this, and then we can start regression. If you want to continue studying tonight, or you have time in the day tomorrow, work ahead watching the videos from this point forward and some of the other ones that I recommended you look at. Let's do this last exercise and then we can go. Area to the right of z should be a small number. That's why I put it over here. So you have to look, what does this say? The area to the right of z, so I have to go in this direction, has to be a small number. So it puts me all the way over here. But that corresponds to the 99th percentile. And I want to write that because the chart gives me area to the left. I've done a horrible job with this. Anyway, that line is not a line. So I look inside and out to find what z is. Carrying out the backward steps. So looking for 0.9900, remember we saw this already, right? 2.33 is the better answer. So let's do the backward problem in Excel and then we'll go. So we already found this answer for the 99th percentile as 2.33 on the standard normal. I asked the question in a different way, but it's asking for the same thing as the previous question. So remember to use the positive table since probability is greater than 0.5. We average between two middle values. If there's no single center, your value must average. Otherwise, if there is no value at all, you pick the one that's closest. That's what we've done. All right, let's try this one. No, let's try this one in Excel. So it's the inverse problem. We tell it the probability and it gives us the answer. It's very, very easy. So let's do, so this is, let's just erase this. And hit equals. Nor and you want the inverse, you want the standard normal inverse. All you have to tell it is the probability. So we tell the probability 0.99, right? 2.33. So that's it. You just put one value. It's very, very easy. All right. Any other questions for now? So tomorrow I'm going to finish normal. We're going to spend about an hour on it, and then I'm going to get into regression. And I should be able to do regression in 3 hours, so I'll have to borrow another hour from the Wednesday's class. So we will pick up here. If you want to work ahead, solving these problems. I mean, watching these videos, I explain all of this. So what we have to do next is go back. So we're going to use the standard normal distribution to help us solve problems with any normal distribution. And I'm going to show you how, and I'm going to suggest that's how Excel programs to find the problems. Or maybe it just uses the function that I explained to you, actually. So using the function, actually I don't know which one it does, but either way, using the tables that I've given you, the standard normal table, we can solve problems So what are we essentially doing? We're making predictions of what to expect from a normally distributed variable. Now this is a basis for probability theory. That's why we learn it now. Okay, it's a basis for Excel. For regression as well. So the standard normal table or standard normal distribution can be used to solve problems for all normal distributions. And it's based in the fact that it's the standard, and it marks with each value, each z-score, you know your relationship relative to the mean. Remembering that statistics is about averages and relative measures, this is what we try and establish a foundation in the idea of working with relative measures. When we talk about the mean with symmetric distributions, we relate everything back to the expected value, the mean. So that's it. That's all I'm going to say for today. If you want to work forward, and tomorrow will be a bit of a review. And you have the homework exercises to attempt and the quizzes to try. So go on and work ahead, and then I'll clarify any questions tomorrow within the first hour. Also, if you have any questions you want me to solve on the test, let me know, and I can look at those in the first 10-15 minutes of the class. The next test, unless there's another disruption, I will have the test posted just for 6 hours on Saturday, and that should be, I hope that's enough time, but we can talk about it, like I said, towards the end of the week. Okay, good night, everybody.